Good day, I'm Max. I work at WhatsApp, focusing mostly on performance and scalability. I joined WhatsApp in early 2016. It was by that time already huge. It was serving 1 billion active users and delivering more than 40 billion messages every single day. Many papers of that age were fascinating. How a small engineering team, estimated at 50 people, managed to achieve that. But what these papers didn't say is that server team was actually just a small fraction of that 50. We've been performing all the duties. We've done everything from re-imaging bare metal servers to doing statistical analysis over some country engagement or so. I even remember filing like a fancy support tickets at IBM software company that we've been using. Hey guys, could you please re-grease the CPU number 2 on that machine because it seems to be missing thermal paste and therefore the CPU throttles under heavy load. To their credit, that service was really great. So they were even sending updates like, hey, our technician enters the building, our technician pulling the server out of the rack, and the technician removes the cover, the technician puts the more of that thermal paste and moving it back and like assembling it how it used to be. So we learned to solve those problems. It was possible because we minimized the amount of moving parts, or rather parts at all. We ran our machines as bare as possible and our infrastructure as lean as it could get. And our core, Erlang, we ran it untouched for many years. By the time I joined WhatsApp in 2016, OTP version that we used was already 3 years old, and there was about 100 patches on top of R16 release. I was truly impressed. I can recommend watching earlier Erlang Factory talks by Rick Reed from 2012 to 2014, just to see the amount of work done, but not contributed back. And by now, all the patches are nothing but history. There is nothing left to share. So skipping 5 years, WhatsApp is by far the most popular messaging platform. We deliver over 100 billion messages a day and we serve more than 2 billion users. And that we are now using the latest OTP version, which may or may not even be close to official release. How could it happen? What caused the change and what lesson did we learn? My talk is about this journey. Such change doesn't happen overnight. We continued to backward R16 patches even in 2018. That means we have been supporting 5 years old platform. Our fork had short of 200 change sets, consisting of mostly bug fixes or some new features or some scalability improvements and some stuff that we backported from later OTP versions, mostly for performance reasons. For example, we had crypto application changes that were enabling hardware acceleration in OpenSSL. We also had some scalability patches about PG2, major, global, and SSL. Some changes were very simple, like sharding its meta table into smaller portions to avoid lock contention. We had a lot of that lock contention because we were running beefy machines with 56 cores, like dual socket machines. In addition to these patches, we had some that were really messy. For example, we had a patch that was dropping messages from the process message queue, or we had patches that were breaking guarantees and letting some messages to be rearranged in the receiving process message queue. And of course, we had bug fixes. So we knew the system in and out, and we were able to run our machines very efficiently. But we clearly realized that we would need to scale further, and that would lead us to the cloud. Since we were already a part of Facebook family by that time, we knew that we had to evaporate into Facebook private cloud. So it happened to be the most challenging process we went through in 2018 and 2019. We had to replace a lot of underlying componentry. So first and foremost, there was no option to continue with FreeBSD. And all our fine-tuning experience was useless. So, and then next, we lost control over hardware that we were using, and we lost control over lower level stack. We could not freeze the world. We needed to learn how to live in always changing environment. And lastly, we had to learn how to coexist with other services running next to our containers and other things happening at the time while our software is running. Just one thing remained: Erlang language, its runtime, ARTS, and OTP, Open Telecom Platform. We had some really amazing time running the same source code on bare metal FreeBSD machines and inside Linux containers. Just one problem we had: we could not get the container performance nowhere near close to bare metal servers. So our primary metric was, and the thing still is, the number of locally connected users, which means how many phones are talking to a specific Erlang node right now. That's roughly equivalent to the amount of TCP connection, and that's extremely dependent on network stack performance. We were routinely running 500,000 connections with FreeBSD and had some headroom to spare, but with Linux containers, even the beefier ones, we could not achieve even 200,000. And the major bottleneck was the single poll thread that OTP16 had. Like, just imagine 1,000,000 sockets that you have to operate through a single ePoll file descriptor. And interesting that OTP21 brought enhanced I/O scalability, which indeed was multiple poll threads and ePoll descriptors. Was it the only reason to make the leap from OTP16 to 21? No, I don't think so. It was just broke the camel's back. And we started the upgrade process, which lasted well over a year. We are in the government. We just cannot raise the debt ceiling infinitely. So we had to kind of repay that debt that we incurred. 5 years of neglecting these updates and almost 200 custom patches, it presented a serious challenge, although different from what I originally anticipated. So unbelievably, but OTP16 and 21 retained external term format compatibility. Our production cluster was running OTP16, OTP20, and OTP21, and they all worked together. Some communications were limited. For example, we couldn't send lambdas funds over distribution, but it didn't really affect our daily operations. We also didn't have to solve the bytecode compatibility because we were just packaging source code, delivering that source code to production machines, and building it there, right on production machines, on every single machine. It's not exactly a cloud-native approach or container-friendly, but it did the trick. So we needed the same source code to be compiled with OTP16 and 21, and we had to provide various adapters. Nothing uncommon. The major hassle I remember, and I put it on a slide, is the get stack trace deprecated, and so we had assorted get stack with stack all over the code. There was another genFSM deprecation, so we ended up suppressing it for a couple of years, and it seems like it's still chugging along there in OTP25, probably even longer. Yeah, but back to upgrade. We found that runtime behavior also changed a lot. For example, async threads that were used for file operations, they were no longer in use. The VM configuration parameters changed. We had to re-evaluate many assumptions that we had about Erlang performance. Many myths were retired. And when we proceeded to large-scale deployments, we ran into VM crashes. Reading bean core dumps is not an easy task, given the lack of documentation and like fastly evolving VM. Actually, I cannot express how grateful I am to Lucas Larsson, who helped me to do my very first VM debugging session. That was a blast. Yet the main challenge was our own pile of custom patches. So when I joined, I saw that pile as a sign of an excellence. Hey, we can do better than a dedicated team. It's later I realized how heavy the burden is to have that 200 patches with no tests, no explanation what these patches do, and no clue like whether we need them at all. Most patches could not be merged without a rebase conflict, so they had to be rewritten. I spent a huge amount of time cherry picking, squashing, re-implementing, rewriting, redoing, and ruthlessly dropping everything that I could. After that, just about 60 patches survived the purge, and like the rest was just dropped. It took us about a year, but we were lucky to get to OTP 21. I thought that it will be the end, so like the next updates will be released, and I thought maybe we can postpone it for a while, and it was wishful thinking because like the second update iteration started right after we finished moving to 21. And the reason was simple. So our cluster had to grow several times in size because we were replacing like the beefy servers with low power machines. And we were expanding into more data centers, into more regions. At that time, we were relying on heavily modified, but still PG2 mechanism, which had ordered set under the hood. And every significant update in our cluster or restarting a couple of thousand machines, it was causing a severe lock contention because of how ordered set was implemented before OTP 22. We even introduced some denormalized copies of PG2 tables to manage that problem. OTP 22 had that thing solved. As you can see on the graph, it became a lot more concurrent with ordered sets. And they also brought a lot of other goodies. For example, the distribution no longer suffered from head-of-the-line contention. And we were able finally to remove our own I would say, fork of Erlang distribution that we were using for pretty much most of our communications. It still suffered from lots of other problems that have been already solved within Erlang distribution, like security, some of that security, and head-of-line contention, and many other things. It was just faster. Erlang distribution is pretty good. So I must admit, I was hoping for an easier job coming from 21 to 22. It wasn't too bad, but it was still challenging. Deprecations were no longer problematic. We didn't need any source code adapters or changing VM configs. So we were only down to two things, custom patches and bugs, core dumps, stack processes, memory leaks, everything like that. Originally, I attributed this to OTP 22 being just very fresh from the oven, like never used 0.0 version of anything, just wait until 0.1 or 0.2 or something, and then use it. But later analysis showed that it's not the case. Most problems were actually happening in previous OTP versions too. It was our own software that evolved. It started using more features. It started to rely on new behaviors, and it was exposing more bugs, not necessarily in 21 or 22, just in general. And the custom patch maintenance, it was a self-inflicted wound. Bugs, there weren't. Bugs were there. But I simply could not go and report, hey, you got a bug in OTP or in the bin. We had so many of those patches modifying VM behavior that it made no sense for me to even try reporting those bugs. But core dumps of these bugs, they were happening in production. And I couldn't upload the core dump, and I couldn't even run the unmodified VM there because our software was relying on these modifications. So by that time, I clearly realized how detrimental it was to use forked OTP. We were backed into a corner, bound to fix all issues on our own. But at least we learned the lesson and learned to do the right thing, to actually contribute to upstream. Half a year after official 22 release, we upgraded all our services to that version. And we contributed more than a dozen patches upstream to OTP. By that time, we accumulated a lot more knowledge about Erlang and OTP in general. We also knew the yearly cadence, and we knew another big update was coming. So as soon as 23 release candidate happened in February 2020, we started testing it before the official release. There was no specific feature we were after, but we were looping in our own contributions, for example, process groups. Important motive for us was to find and report issues and bugs before those bugs made it to official release, because it's just easier to fix it. Otherwise, after the release, it's hot fixes, it's like problematic API changes, backwards compatibility, all of that. So as expected, we still had custom patches, and they happened to be the most frustrating problem. I fought it bravely and managed to bring it to like 15 or so. And this was primarily achieved by modernizing our own code base. Most of the patches that we have, happened to be unnecessary. The same result could be achieved without modifications. And the only challenge was scale and lack of paper trail from the past. It was just impossible to know why we implemented that patch or whether the modification makes sense at all. To give a trivial example, we had the patch that was expanding one of the lookup tables, presumably to fight block contention. But there was no actual data or a test case or anything that was confirming that block contention actually happens. It might have been 8 years ago or 10 years ago, or it might not. It could have been an assumption that has never been verified. This is actually how I learned to be more generous with test cases and comments in the source code. Long story short, we had OTP 23 everywhere in just a couple of months after official release, and that was in the middle of pandemic, summer 2020. Which changed the world a lot. It's no secret how video conferencing companies grew. I envisioned their challenges were much higher than ours, but we still attached more users. And we also anticipated server supply shortage. So we thought more about efficiency. The projected growth would put our cluster well beyond 40,000 machines. That's a lot. That's a lot of machines. And we were anticipating difficulties in getting that hardware. It's not just cars that you cannot go and simply buy the servers. They work the same. You can order some, but you never know when they're going to be delivered. So we knew we should take a closer look at how good our software is and the performance. We were already looking into server efficiency when the Maxim JIT was published as a pull request to OTP. And I have never seen so many thumbs up on that single pull request. The JIT happened just in time for us to support the growth. We went ahead and progressed beyond official OTP 23 releases and just included the Maxim itself. We based our build on top of OTP master branch, and the upgrade went smoother than ever. I guess it's because summertime is vacation time in Sweden, so there weren't many other changes, but either way, it worked. And by the end of November, we had JIT deployed everywhere, and it reduced our CPU usage by an average of 25%. It was the first time for WhatsApp in WhatsApp history that we did not expand our production clusters to accommodate New Year's Eve spike. Since that time, we were decoupled from official release schedule for OTP. We were able to utilize improvements continuously. The crusade against custom patches made that thing significantly easier. So we were only concentrating on issues that manifested at scale that maybe no other company has, and only on some specific workloads. For example, we were pushing gigabytes both ways through Erlang distribution, or we were establishing like thousands of outgoing TCP and TLS connections. So we were mostly targeting these. It was much easier to get the root cause of problems if we were to find any, because we were no longer reading 5 years worth of changes and our code no longer depended on custom patches. We were running vanilla OTP in production, and we could join forces with OTP team to actually root cause and fix bugs before they made to official releases. And that made us to employ upstream first approach. So if we need to change anything in the beam or OTP, it must be a high quality contribution that passed OTP team and community scrutiny. As soon as that patch gets merged, we no longer need to have it in our custom queue. And if the patch is not accepted, chances are we don't want it either. Where we are at now, we still have 2 functional patches to the VM, one that exposes per process message queue statistics. That's basically how many messages were sent to that process and how many messages the process extracted. We use it to detect some processing slowdown or various issues when our code does not make the progress that is expected from that process. So that's why it's different from just amount of messages that's in the queue. And we've got another patch that speeds up VM level summary that provides a sum of all queue length and the process identifier that has the longest message queue. The rest are just a couple of bug fixes. They are already on their way to upstream. Now, having completed this upgrade journey multiple times, we established more or less formal approach and formal upgrade process, and I'm going to share this expertise. There are dragons on that road to get the latest and greatest, but you can tame them just the same way as we did. Tame and harness with continuous integration. As I already mentioned, we have a fork for the repository, or rather two forks. One is available externally on GitHub. You can just go and see what's in there, but it's largely unmaintained because GitHub just does not provide necessary integrations. In our daily work, we rely on internal Git repository. Hence, all our upgrades are starting with rebasing on top of either release branch in the past or the master branch right now. Our build employs additional features that are turned off by default. For example, extra microstate accounting states and dtrace with system tap. I briefly talked about it in 2019 talk in San Francisco to explain why we're using those. We're also keeping frame pointers to have better visibility into core dumps and to be able to use Linux curve utility. That's very helpful for performance investigations. So this configuration actually doesn't seem to be tested in OTP Team CI, and that's why we are running our own here. So sometimes we actually see broken builds. In some cases, VM code wouldn't even compile. It usually is a trivial fix, so if we submit it, it gets merged almost immediately, but still, it's an interesting work. So after we rebase remaining patches on top of master branch, we run OTP test suites, those that are coming with OTP itself. And if there are no unexpected, I will explain what is unexpected, test failures, we make that release candidate and then we use it to build WhatsApp code base. And that stage, we may discover that some APIs have been deprecated, and that's why we need to update our code base to to address these deprecations. And then we run all automated tests that we have for our own code base and perform a number of canary deployments. But the last step, it sounds innocent, slow rollout or gradual rollout. It's actually the most complicated one. We have over 100 of different services with wildly varying workloads. So firstly, from 16 to 21, required careful consideration on the number of reverts, re-reverts, and moves forward, and all sorts of juggling various versions. But subsequent updates were smaller, they presented less risks, and they were still taking long. Why? Because the manual process is not great. First, every single time it's an exhausting marathon. It's lasts for months. Every time we had to carve a different path to our own services. It could be service by service upgrade. It could be moving multiple services at once or updating a few machines and waiting to see bugs. That was not easy. And we lacked visibility. We couldn't reliably see the rollout percentage, or we couldn't even know what versions were running where, or in production or in development machines. So if something also fails after we upgrade OTP, we didn't have proper attribution. We couldn't say, did it fail because we updated OTP or because the service was broken? Not by us, by someone else, unrelated change. What we did, we introduced automation. We introduced CI for OTP itself. We wanted to have that process reliably repeatable. We wanted to have smaller and obviously more frequent updates. So we tried to automate it. And of course, first thing we did, we automated test runs. The glorified cron job just pulls updates from GitHub. If it breaks, then it asks for human to help. Hey, please resolve the merge conflict. We have seen just one or two because we don't have many patches right now. Then if that finishes successfully, we built OTP and we run OTP test suites there. Then we upload the OTP test results into an internal database that keeps history of all previous test runs. So we know which tests are permanently broken, which are flaky. That means they're sometimes passing, sometimes not. And we know which tests were broken or started to fail after the latest update. We skip testing applications that we don't use, for example, SNMP or diameter, and we disable tests that are permanently broken. For example, those assuming specific time zone. Tests still run, just we don't get notified about any failures there. But we always investigate tests that just started to fail. We investigate those failures when that failure is detected. We have automation that files a task to deal with. Sometimes it's a genuine problem, sometimes it's a transient problem or an unrelated change in our infrastructure. But at least we can easily see when there's a build broken, when there's a test broken, where is microstate account not working. We see that. So unfortunately, our internal tooling doesn't offer good support for anything else other than CentOS-based Linux. And we are using only IPv6 machines. So some applications in OTP, like SSL, they assume that IPv4 is available, and therefore they fail half of the tests they have. That's kind of another thing that we accidentally found. So if we detect no new failures in OTP test cases, our pipeline proceeds to building our own code base, the WhatsApp code base, starting with third-party dependencies. We don't have many, but those we have, we actually try to support and maintain. For example, we can even make some pull requests to adopt to a new, not yet released OTP version. Then we run all tests that our own code base has. This process works from the separated from the primary CI, because we don't want to mix signal when we update OTP and when we just run our code. And then if all tests that we have for our own code base, they pass, we mark that OTP build as passing. And then we may do a canary deployment just to be sure that there is nothing that we just don't know about, just to get some more confidence. If we have more confidence in that automated quality testing tools, we probably would skip that, but it helped us to find a few issues in the past. Then we also have automation that rolls out the new build or the new release, the new, not official release, but the new build. As I already mentioned, production stages tend to be convoluted, tend to be risky. There is still no consensus of whether we should make it absolutely automated or we should have a human that clicks buttons. And we decided that we want a human to be at least a person, at least there is a human who clicks that thing. So like engineer observes the process, triggers next rollout steps, just, maybe it's not necessary, but that's what we have. Over the year, we converged to a staged rollout procedure, starting with non-user facing test environments. These are actual production machines. They run shadow or synthetic traffic. Then we get to the second step, which involves testing on a single instance of every production service. This allows us to monitor all workloads without sacrificing reliability, because we know our cluster is built to tolerate long-term unavailability of a single machine. If that completes successfully, then we proceed to upgrade all machines in a single region. At that scale, we run thousands of machines with a new version. Failure is still tolerable though, because we are routinely testing region failover and we have confidence that disaster recovery actually works. If you don't, I suggest that you start doing it now. Then if that single region testing takes longer, but it ensures safety of the further rollout because it's already thousands of machines. And then the next step is obviously to take this version to all regions, all services, all production stuff that we have. And only then we unleash developers and let them use the new features supported by new OTP versions. And only then we change the version in our primary CI. What failures do we see? Every step of the upgrade process can fail. And just like in all computer games, if that happens, you get the game over sign and you have to start from the very beginning of the level. With most of custom patches gone, we rarely get rebase conflicts. I think I can remember just one in this year. It used to be a serious pain, but that's no longer. Same for incompatibilities that are caused by old code deprecation. Since we don't jump over a version, handling deprecations is easy, mechanical task, I would say. But integrating OTP in our CI exposed test failures that we previously just didn't see. They were always there, just we didn't see those. Those are annoying, but since it happens before the actual build gets out, there is no production risk associated. And the risk of running new builds in test environments is also rather low. But still, if we run into an issue, it may affect actual developers using those test machines. And depending on the problem severity, we may need to return the test environment to a previously known good version. That is, we do that when we see the significant degradation or like bad experience somehow. But if it's just extra spam in log files or like slightly elevated CPU or memory, we just pause the deployment of this version, but we don't roll it back. Most often than not, we actually fix that forward and provide even newer build with these problems fixed. Dangerous things only happen on a production rollout track. And in our experience, it takes thousands of machines to manifest any kind of deep or any serious bug. And at that stage, it's very important to have a properly functioning escape hatch that is a rollback sequence. If we run into any widespread issue, the first step is always to revert to the previous version. And it sometimes happens that the root cause has nothing to do with the real OTP upgrades, but we prefer to be safe than sorry. So what rare failures we see at scale? Some of them are so rare that we can't even proceed with the rollout, even suspecting that there is a bug. The reason is simple. We need a way to reproduce the failure and collect necessary debugging information. Since those problems aren't easy to detect, we have accumulated a number of various practices that actually help us to do. One example is we monitor message queue length. We monitor the sum of those message queue length, and we monitor the longest queue, and we alarm if any of those grows over time. That's one thing. Another thing is log contention. It's easily detected when when scheduler utilization exceeds CPU usage. Of course, we monitor crash dumps, we monitor core dumps, but we separate these two. In most cases, crash dump is caused by our own code, and it is investigated by the team that owns the service. But core dumps are different. It is a privilege or a burden of just a handful of people to look into these core dumps. Yeah, and when we get one, when we realize, okay, that's a bug, that's a problem, first thing we do is we reproduce it. We reproduce that thing in form of a test case. It's usually the hardest part. In the past, we often neglected that step because it was too complex. But yeah, in some cases, it's actually harder to make a test case rather than to fix the problem. But now we know that we are going to merge the fix upstream, and we are absolutely sure it's the test case first. And it's also much more productive to start with, because that gives us more power to reproduce it, and then we can find a better solution to fix the problem. So we naturally adopted test first approach in a sense. Yeah, so we ensure that our own tests do not fail in our CI. But what can we do when a failing test comes from like GitHub or from outside, from OTP team updates the actual code there? We can't avoid this. We cannot block a patch that the OTP team merged somehow. Just like we cannot do that. But what we can is we keep track of every failing test case, so we know whether it's been consistently passing or failing. And if we see new failure, it usually doesn't take long to understand why it failed. Usually there is just one or several commits to look at, and if a test case fails and it was consistently passing before, we get notified and we can take appropriate action. Sometimes it's appropriate just to disable a test. One anecdote, there are some tests in OTP that can only pass when time zone of the server running those test cases is either Central European time, which is Sweden, Stockholm, or South Africa Standard Time. I guess someone had been hacking on vacation there in South Africa, working on that. I think there was time suite tests. Anyway, so making the tests pass in our local CI is really not that hard. The real challenge starts later when we move on to upstream. Erlang is supported on many operating systems, and OTP provides nice compatibility guarantees. So anyone planning to contribute would need to recreate a bunch of test environments in various combinations, which is not trivial and is often undocumented. For example, there are tests running previous OTP versions, and they require that they have to be installed into specific directories or locations. Another example is Windows setup. It's really challenging, even though it's complicated, but I think it took me a couple of days to get anything working, and I still couldn't get the OpenSSL part. And OTP tests are painfully slow, so changing one line and running a single test suite can easily take 5 minutes. Running all tests, it may take a day or even more to complete. Since I don't know which tests I need to run and which I don't need to run, I have no choice. I have to run all of them. I also need to remember to run static analysis tools like Dialyzer, Documentation Winter, and other checks. These checks have to be done separately from tests, and so I often forget to do that. And I plead guilty of submitting a number of pull requests with failing those checks. Thankfully, GitHub notifies me that I'm failing those tests, but I'm still feeling bad for that. I suspect it also makes pull requests to be stuck in code review for ages, because I mean, it's not easy to kind of pick those patches, to have it somewhere in OTP CI. I can give an example. I had a pull request opening June 2020, and it was merged only by February 2021. And it's not the OTP team fault. In fact, I actually received a tremendous amount of help from them. The help was absolutely amazing, down to providing some debugging information and like steps to reproduce the problem from some fairly exotic OpenBSD thing. If only I could have that test signal in CI before submitting my GitHub pull request. That's how I ended up with, that's how I ended up with Home Lab setup. I used a community version of GitLab, and it took me just a few hours to have some basic testing automated. So it means that I can now verify my pull requests before opening them against the upstream repository. And I can run a lot more tests compared to what GitHub Actions do. In fact, I can even run all OTP tests. I can run it in multiple Docker containers, sharding those tests, so I can significantly speed up testing the Linux version. I only wish the Docker existed for other operating systems, but yeah, that's a different problem. I would really love to see this done at scale. I would really love to see this done with either GitHub Action or some similar solution. It would really shorten the review cycle, and it will take the burden off OTP team because they have enough other work to do. There are actually highly successful examples of such setup. For example, Apple, they have a Swift language and they have a community CI for that Swift language. And you can even donate your machine to support that, or not donate, but like, I don't know, like not give it away, but rent it or somehow. That's one thing. And it's just the beginning. The whole testing story can be told very differently. Just imagine how great it would be if you have test signal ready in just a few seconds or minutes after you're done typing. I know it's possible because we have it. And I know it's possible if we work to improve the existing framework. What I mean is, yeah, we can talk about static type checking, static analysis, modularity, code formatters. We can talk about namespacing, but when it takes days to fix a trivial typo, the productivity will be limited. Time is the least thing we have of, said, I think that was Ernest Hemingway. So rethinking Erlang testing framework can raise the development velocity to the next level, starting with actually refining test model. What is the artifact we are testing? How do we configure test environment? How do we configure things like multiple OTP versions or even previous versions of our own code? What are the conventions to put the temporary files, test fixtures, long-lived state, or like test run history? Common test is the framework that we, WhatsApp, adopted successfully, but it can be improved in so many ways. There are all those things like smarter assertions. I guess Elixir people, you have a few words to say. There's also, would be great to have better test isolation. So how many times did you see a test failing because some other test left garbage in the VM state 20 minutes ago? I've seen that a lot. So now, if we can have better isolation, then we can also leverage concurrency. Like, in fact, I would expect common tests to run as many tests concurrently as my CPU and my RAM allows. After all, like Beam is all about concurrency. And like why the common test is painfully sequential. Why is it running test cases one by one? It feels more like 90s rather than 2021. And I feel the same when I look at common test HTML output. It is quite convenient for manual analysis, but it's old-fashioned and making it hard to feed test results into automated processing framework. I know about CTI Surefire, we use it, but it's still not the best solution, I think. But can you just imagine if we can push test results and test coverage data into a tool that maps source code to actual test cases? This is how we can get the automated test selection, so I don't need to manually know which tests I have to run. We have that experience within WhatsApp. Our WhatsApp code base is actually using this approach. And it's a very positive thing to have. We shortened the time to get test signal, like, I think by half or even more than that. That leads us to the incremental future with fast and quite convenient testing, not just for OTP, but everything that's built on top of it. I can't tell for everyone, but it would surely incentivize me to make fixes in OTP rather than workarounds that we have in the code. And if we have that comprehensive community CI, testing my pull requests in all supported environment, that would be so much better. I won't need to bother OTP team asking, hey, did I break anything in your build, in your CI? Or like, is it okay at all? I already mentioned that Apple has Swift language doing that. It's not the only example. I think Golang does the same thing. They also have some community, and that community grows rapidly. I do believe that community contributions will become, or becoming the primary driving force, evolving the language and the ecosystem. And if we evolve that, we can then probably drive the release cadence faster. Just look at Rust. They have a release every 6 weeks, like a clockwork, they say. And it's just easier to digest a smaller updates. Like, I would imagine Erlang could do that. Erlang could do monthly cycles, except, I guess, August to honor traditions. But yeah, why not? All this and many other exciting things we can build together if we work hand in hand to strengthen the core, the base, the foundation of the ecosystem, which is OTP. Whether you're just learning a Beam language or you are defining a corporate guidelines for thousands of employees, we can find a way to collaborate. Join Erlang Ecosystem Foundation. It's good. It's good. Let's meet each other and get to know each other and help each other to build this thing. Or join me at WhatsApp and let's go build it together. Go build our own future. I'm sure we can do it.